Hello, I'm Julian Wharton. I'm here to introduce the Naval Engineering theme within the Mechanical Engineering programme taught here at the University of Southampton. A naval or marine engineer is someone who designs, operates and maintains machinery and equipment used within ships, offshore installations or any other maritime infrastructure used elsewhere at sea. Naval engineering is a field of expertise which combines other engineering disciplines, as you might expect, such as electrical engineering, engineering design and optimization, and other control technologies. The field is closely related to other similar subjects such as naval architecture, which is also taught here at Southampton. 90% of globally traded goods are still to this day transported by sea, and that roughly equates to 10 billion tonnes per year. However, viewed largely from a distance or hidden from us beyond the horizon or indeed beneath the ocean waves, we sometimes fail to fully appreciate the sheer scale of these engineering achievements. Shipping and maritime platforms are colossal engineered structures, hundreds of meters in length and may be hundreds of thousands of tons in weight. Here we have examples of container ships which regularly dock in Southampton, visiting the container ports. These types of vessels can transport in a single go 7,000 to 8,000 containers. These are the containers we see on the backs of lorries going up and down the motorways. This image here shows the transverse bulkhead for a container ship during construction, and to give you a perspective of scale, there's a figure standing on the top deck here. During construction, the sections of the ship are often painted, and that gives us a perspective of the waterline during operation. And we can see that there may be 4 to 5 levels below the waterline, which will be filled with containers. Equally, or above the top deck here, there will be stacks of containers, maybe 7 to 8 high, to give you the full complement on board ship. Although these are complex structures, they are constructed from fundamentally simple engineering principles and engineering elements such as plates, beams and flanges, all of which are taught within the first year of our engineering programme. And we've got examples here within this figure. Here we have cranes. These are the tallest structures in Southampton at 130 metres. Again, they're using simple engineering principles, in this instance cantilevers, to load and unload the containers from the ships. Again, this is taught within the first year of our degree programme. Moving on to marine propulsion, marine engines to power ships are equally enormous, as we can see here in this illustration of a 2-stroke diesel engine. The piston, which is just here, is approximately a metre in diameter, and when in operation these engines will use about 100 tonnes of low-grade fuel oil a day, which will often need to be sieved to remove the sand before going into the combustion chamber. This low-grade fuel oil in future will need to be replaced with a more environmentally friendly alternative. Currently, in the short term, this could be methane, although to move away from fossil fuels altogether, this could be either hydrogen or ammonia. For a ship to move in the sea, it has to have a propeller, but this means that there's a hole in the hull. To support the load of a 40-ton propeller and to allow unrestricted and smooth rotation of the propeller shaft without seawater ingress, we have something called a stern tube. So we've got an example here. This is heavily engineered to support the total weight of the propeller on the shaft, and this is supported by the stern tube bearings, which are these orange zones here. These are complex sets of seals to limit the water ingress into the hull, but equally it stops oil from leaking out and contaminating the sea. Modern versions are now using compressed air and seawater lubrication to comply with new environmental restrictions. Moving on to key naval engineering themes. This is built upon, in terms of the Part 1 and Part 2 modules of thermofluids, fluid mechanics, structures and materials. This leads us into the Part 3 naval engineering modules, such as fundamentals of ship science, which overviews the fundamental concepts that underpin fluid interactions and forces on maritime structures. Marine structures develops further skills needed for design and analysis of maritime structures. And equally, we have marine engineering, where students will learn about the operational principles, machinery configurations, and efficiency measures that are required in the design and analysis of marine engineering systems. These will be also complemented by other optional modules from materials for transportation, maritime craft, concept design, and also tribology for future mobility, which would cover issues associated with stern tubes and large-scale gearboxes, which are used in ships and also in wind turbines, which I will discuss in a minute. Other options to support this theme will be composites, vehicle powertrain, and noise and vibration associated with the machineries of operation. As I mentioned, other case studies associated with naval engineering are the offshore wind turbine arrays, which have received a considerable attention in recent years as green and renewable energy sources. Again, these operate in the harsh marine environment, so to be cost effective, they need to have minimal amount of maintenance over their expected 20-year lifespan. From an engineering point of view, this is really tricky. Ever wondered why turbine blades don't turn? Well, here, the gearboxes, we've got examples here, transfer the torque of the rotating blades, which may be rotating at maybe somewhere between 5 to 20 RPM, and uprate to a high speed output of between 1500 to 1800, suitable for the AC generator. This low speed, high torque is applied to relatively small contact patches of maybe just a few centimeters within the planetary gears, and the lubrication films are only just a few microns in thickness. So this is an extreme engineering challenge, especially since any dynamic fluctuations from the blades will be translated onto the main shaft bearing here, and you can unload the main shaft bearing, which will then translate these forces onto the planetary bearing, and then that will compromise the gears and the lubrication regime within these types of engineered systems. So here we've got an example of an 8 megawatt first stage planetary gear, which would be situated just here within the wind turbine. So moving on to facilities specifically available for students on the naval engineering theme, these include the Boulderwood fluids labs, where students can use the various hydraulic benches during teaching labs to explore engineering principles associated with fluid mechanics. That would be the Reynolds apparatus, Bernoulli's theorem, hydrostatic pressure and forces, and fluid channels. Equally, there's the towing tank, which students could get access to as part of their third year individual projects, or indeed their fourth year group design projects, which they compete with over the last year of their degree program. Okay, that's the end of my introduction. Thanks for listening.